Okay, so we have seen the insertion and deletion operation in balanced binary search trees. Okay, and basically we discussed hide balanced binary search trees. There can be several types of balanced binary search trees. Till now, we have discussed hide balanced binary search tree because the definition of the balance of a binary search tree is defined in terms of the height of the subtrees. Okay, so what I mean that balance of a node is defined as the difference between the heights of its left and right subtree, right? So this kind of tree, where heights of the subtrees are used to define the balance of a node, is called height balance binary search. There are also other balanced binary search trees. Okay, we can define weight balance binary search tree instead of height balance BST. So in the weight balance binary search tree, we use weights of the nodes to define its balance. Okay, so what is the weight? Okay, weight can be anything. Okay, you can define the weight of a node in different ways. The most widely used definition of the weight of a node is, that is, say, first I draw a node, I draw a tree, right? For example, this is your tree. Okay, this will be a balance. This will be a weight balance binary search tree if the weight of each node of this tree is the 1, 0, minus 1, not more than 1, right? So first you define the weight of each node. So you can define the weight of each node as the number of nodes in the subtree which is rooted at that node. Okay, for example, consider the root. So the weight of the root is the number of nodes in the subtree which is rooted at this node, at the root node. Okay. So this entire tree is rooted at this root node, right? What is the number of nodes in the entire tree? 1, 2, 3, 4, 5, 6, 7. So weight is 7. Weight of the root node is 7. Now consider this node. Okay. What is the subtree which is rooted at this node? This tree, this subtree. Okay, the root of this subtree is this node, right? So what is the weight of this node? The number of nodes in the subtree which is rooted at this node. Okay, so this subtree which is rooted at this node contains only two nodes, right? So the weight of this node will be 2. Okay, now what will the weight of this node? Okay, what is the subtree which is rooted at this node? This one, and the number of node is 4. So 4. Okay, for this node, left and right subtrees are empty, so only one. This is also leaf node, only one. Leaf node, only one. For this node, the subtree which is rooted at this node contains two nodes. Right? Okay. So this way you can define the weight of the nodes, and then you can define certain criteria which defines the balance of the tree. Right? So I'm not going to discuss the white balance binary search trees, another kind of balanced binary search trees. Right? I just want to discuss that these kind of trees are also exist, which are balanced binary search tree. Another kind of balanced binary search tree is red-black tree. In the red-black tree, we use different criteria to obtain the rotation operation for to make a binary search tree, to make an unbalanced binary search tree balanced. Okay, so what we do, we define two colors, red and black. Okay, so a node can be the red or black, right? So only two colors are possible. So each node must be colored, and the only two colors are possible. A node will be the red color node or a black color node. And And then we define certain rules, we define certain criteria. For example, uh, which color node, whether the red color node can have a black color node, okay, or a black color node can is allowed to have a red color node. Okay, so these kind of rules are defined. Okay, and when these rules are followed, the obtained binary search tree is always balanced. Okay, so we will not discuss them in detail. I just want to introduce that these kind of balanced binary search tree also exist. Okay, if anyone is interested, he can you can use that weight balance binary search tree is also discussed in the Tannenbaum book, and the red black tree is discussed in your algorithm book. Okay, that algorithm book that you will use in the third semester. Okay, that is like 4 months, right? Or any other resource which is available on the internet. Now, multi-way search trees. Okay, binary search trees. These are binary search trees because a node can have at most two children, right? So that's why it's called binary search tree. Okay, if you allow a node to have more than two children, okay, for example, that is the number of nodes, the maximum number of children that a node can have is m, right? So in that case, your search tree will be called m-way search tree, right? In the binary search tree, only two ways are possible. Either you can go into left or right. But in the m-way search trees, there are m ways in which you can move from a node to one of its children. Okay. So multi-way search tree, right? Multi-way means there are more than two children. If there are exactly two children, then that search tree will be called binary search tree. If there are more than two children allowed, that search tree will be called multi-way search tree. Okay. And if you know the m, that is the maximum allowed number of children, then you can call that multi-way search tree also as m-way search tree, where m is called the order of the search tree. Okay, so for a binary search tree, m is equal to 2. Okay, so the order of the binary search tree is 2. If three children are allowed, then the order is 3. If maximum 5 children are allowed, then m is 5. So order of the search tree will be 5. Okay, so multi-way search tree are generalized version of binary search trees. Okay, the number of comparisons in searching is of the order of height of the tree. Okay, in binary search tree, the complexity is equal to the height of the tree. And what is the height? The average height is log n base 2. Okay, why 2? Because two paths are possible. Okay, log n base 2. In the m-way search tree, n paths are possible. So using the same logic, we can say that the search complexity in m-way search tree will be log n base m. Okay, that is both the best case and the average case. Such complexity in the m-way search tree is order of log n base m, right? And obviously, when m is greater than 2, then r log n base m is smaller than log n base 2. Okay, so complexity of searching in binary search tree is log n base 2, and complexity of searching in a multi-way search tree of order m is log n base m. Log n base m is smaller than log n base 2. Okay, so obviously m-way search tree is better than binary search tree, right? Okay, so log n base m is the complexity in both best case and the average case, right? But what is the worst case complexity? Okay, worst case complexity is still order of n. if the tree is skewed. Okay. So if you are inserting the elements in the M-way search tree in either ascending or descending order, you will get right skewed or the left skewed tree. And in that case, the worst case will occur and the complexity of searching will be order of n. Right. So again, like in case of binary search tree, we have balanced binary search tree. Okay, for M-way search tree, we can also define balanced M-way search tree. Right. So we also have balanced multi-way search tree, and several different kinds of balanced search trees exist. Okay, we do have different kinds of balanced binary trees. We have height balanced binary trees. We have weight balanced binary search trees. We have red black tree. Okay, these are examples of balanced binary search tree. Okay, similarly we have different kinds of balanced multi-way search tree. Okay, examples are we have B tree. Here B is for balanced. Okay, so balanced tree in short, B tree. We also have B plus tree. Okay, and we have B star tree, and several other versions are can also be defined. Okay, so the original structure of nodes in all these variations B tree, B plus tree, and B star tree are same. Okay, that is the you can see that the difference lies between how many elements can be stored in single node of a multi-way search tree. In the balanced binary search tree, at any node, only one value is stored. That is, a node can have at most two children, left or right. Okay, and in any node, only a single value is stored. Okay, so and m is two in binary search tree. But if m is more than two, for example, say if m is three, maximum three children are allowed. Okay, so, so what will you have? The number of entries, the maximum number of entries in any node will be m minus 1, 3 minus 1, 2 in this case. Okay, so 4, 7. So here you have entries 2 and 5 and right. So this is a multi-way search tree. Okay, so you have two entries in the node. Okay, and maximum three children. That is three edges coming out of any node. Okay, so this is search tree because the 2 is less than 4, 5 is greater than 4. Okay, this edge is to the right of this entry. Okay, so it will be larger, and 5 is to the left of 7, so 5 is less than 7. Okay, and 8 is at the right of 7, so 8 is greater than 7. Right, so this is the multi-way search tree. Okay, so number of entries stored in a node of M-way search tree is m minus 1. Okay, so how these different variation of balanced multi-way search tree B tree, B plus tree, and B star tree differs. Okay, the difference lies in how many entries are allowed to be stored in a node of the balanced M-way search tree. Right. So, for example, in the B tree, there is no restriction. In the B plus tree, all in node can be only 50% full. Okay, so if m is say 9, so number of entries will be m minus 1, that is 8. Okay, so 50% means 8 by 2, 4. The maximum in balance in B plus tree you can have at most 4 entries in a node. Okay, right. So obviously, and we do also have different criteria for internal node and external node. Okay. In B star tree, a node can be at most two-third fill, that is 66.6% can be full. Okay, so different rules are specified for different kinds of balanced multi-way search. Okay, so again, we will not discuss these trees in this course, but we will discuss them in the database course, which will be uh, taught in the next semester. Okay, because these balanced binary search trees are used as an index file. Okay, so where because index files are used for searching. Okay, for searching for the database files. So in the databases, we can have a very large sized database file. Okay, so to search the very large database file is not so obviously not because the complexity is very high, even if you are using a binary search order of log n, okay, or order of log n base m if you're using m base search tree. Okay, the complexity will be very high for a large file. Okay, in that case, we use B trees to keep the height of the multi-way search tree and way search tree balance, right? So we will discuss them in the database course. B tree, B plus tree, and B star. Okay, now Huffman algorithm. Okay, Huffman algorithm uses extended binary tree. Extended binary tree is also called two tree, right? So what is an extended binary tree? Extended binary tree where the number of children is either 0 or 2. A node can have either two children or no children, right? In a binary tree, okay, in a normal binary tree, a node can have either one child or two child or no child, right? But in extended binary tree, a node has either two children or no children, right? So Huffman algorithm is a method for building an extended binary tree or two tree with a minimum weighted path length from a set of given weights. Okay, so what is the minimum weighted path length? Okay, you know what is path length? Okay, so what is path? Path is from the sequence of edges from a node to any other node, right? So, but when we talk about the Huffman algorithm, we talk about the path from the root node to any other node. Okay, and the length of that path is the number of edges which lies on that path, right? So now consider this example, a simple tree. So what is the path length for this node? Okay, 1, 2. This is the path of the root to this node. So the number of edges on this path, 2. For this node, 1. For this node, 1. For the root node, 0. Okay. So, so these are the path lengths for each node. And what is the total path length of the tree? The sum of the path lengths of each node. Okay. So this is called the path length of the node, the path length of the tree. Okay. So this is 4. Right. Now the weighted path length. Okay. When the weight of each node is defined, we multiply the path length of that node with its weight. Okay. And that total is called the weighted path length. Okay. For example, say these are the weights of the nodes. Okay. So at the left, I have written the weight, and at the right of the node, I have written its path length. Okay. So the weighted path length will be, okay, for the root 2 into 0, for this node 2 into 1, for this node its weight 3 into its path length 1, for this leaf node 4 into 2. So this sum is the weighted path length of the entire tree. Okay. So weighted path length. What is minimum path length? Okay. For a given number of nodes, different kind of binary trees, different kind of extended binary tree can be constructed. Okay. So and for those different extended binary trees, the weighted path length will be different. Okay. So Huffman algorithm basically construct a extended binary tree with minimum weighted path length. The Huffman algorithm is an algorithm which constructs an extended binary tree with minimum weighted path length, right? And this algorithm has a lot of uses in different practical situations. We will discuss one one application which uses the Huffman algorithm. Okay, in the coding theory, okay, Huffman algorithm is used, and the code obtained using that Huffman algorithm is called Huffman codes. Okay, so this is the method for construction of minimum redundancy codes, application to many forms of data transmission. Okay, it is used in codecs such as JPEG and MP3. Okay, so Huffman algorithm, a set of nodes assign the values fed to the algorithm. Initially, two nodes are considered as their sum forms the apparent node. When a new element is considered, it can be added to the tree. Its value and the previously calculated sum of the tree are used to form the new node, which in turn becomes their parent. Okay, so this is the overview of the Huffman algorithm. Okay, so in the next slide, we will use them and then it will be clear and better way. Okay, now first see what is the problem. For example, say you have to transmit some data, okay, and the alphabet that is used to construct the data consists of these four characters, ETOA. Only these four characters are used to make the data, okay, and that data is to be transferred over some transmission network, right? So your data message contains just these characters, okay. So now these are the characters ETOA, and the frequencies of each character in the message is 10 for the character E, 7 for T, 5 for O, and 3 for O. That is in the message, the character E is used 10 times, character T is used 7 times, O is used 5 times, and A is used 3 times. Right? So these are the frequencies. Now, since there are 4 characters, how many bits will be required? Because you have to transmit it over the network. So first, these message characters will be converted into binary in the bits of ones and zeros, right? So you must code them in binary. Okay. So there are 4 characters. The most obviously is use 2 bits for each character. Okay. Using the 2 bits, you can find 4 different patterns. Okay, of 2 bits. Plus 2 to the power 2 is 4. So using 2 bits, you can have 4 different patterns like this: 0 0 0 1 1 0 1 1. Okay. So any character can be assigned any code of 2 bits. Okay. So now what will be the length of the total message? The length of each character is 2 bits. Okay. And your message has the frequencies of each character in the message are these. Okay. So 10, 7, 5 plus 3. So 10 plus 7 plus 5 plus 3. These are the total number of characters in the message. So 10 plus 7, 17 plus 5, 22 plus 3, 25. Okay. So there are 25 characters in the message, and each character consists of 2 bits. 25 into 2. The number of bits in your message is 50. Right. So this is the simplest way of coding the characters in the message. Okay. So here we have assigned a bit. We have assigned a bit sequence of 2 bits to each character. Okay. Then the message can be transformed using these codes and then be transmitted over the transmission network. Okay. The size of the message is 50. Okay. Can we reduce the size of the message? If the size of the message is large, then obviously the transmission time will be more, and also the chances for the error will be more because the size of the message is more, right? So if the size of the message is small, then less time will be taken. Okay, the chances of error will also be smaller. So these are the advantages of the smaller message. So can we define some codes, okay, in such a way that the size of the message gets reduced? Okay, here comes the role of the Huffman algorithm. Okay, Huffman algorithm finds minimum weighted path length. Okay, so what we do, we can use the frequencies of each character as weights. Okay, so what we'll do, we will use nodes for each character, and then using those nodes, we will build an extended binary search tree using the frequencies of each node or each character as the weight of that node. Okay, and since Huffman algorithm finds the minimal weighted extended tree, okay, so uh, weight, the obtained weighted tree will be minimal, and using the codes, there is a method to code the nodes of the extended binary tree. Okay, and if we use those codes, then the obtained size of the message will be smaller. Okay, so we will use this example to verify this, whether the size of the obtained message is smaller than 50 bits or not. Okay, so this is the Huffman algorithm. Okay, so what we do in the Huffman algorithm, so initially two nodes are considered, and their sum forms their parent node. Okay, that is the sum of the weights of those two nodes forms the weight of the parent node. So for example, say you have nodes. Okay, so what you do in the Huffman algorithm, in a step of the Huffman algorithm, first you select two nodes. Okay, and which nodes are selected? Those nodes which have the minimum weights. Okay, so for example, say nodes n1 and n2 has weights w1 and w2, and these are the minimum weights among all the nodes, right? So these two nodes will be selected. Okay, these two nodes are selected, and then these two nodes are combined. Okay, that is a new node is created, which is the parent of these two nodes. We can call them n12, right? And the weight of n12 will be the sum of the weights of n1 and n2. Okay, so its weight will be w1 plus w2. Okay, now this subtree, including the nodes n12, n1, and n2, okay, will be treated as a single node. Okay, and its weight will be equal to w1 plus w2. Okay, and then again, next two nodes which have the smaller weights are treated. Remember that this entire subtree is treated as single node. Okay, so this can be selected in this step. In the next step, this entire subtree can be treated and selected as a node. Okay, and its weight will be w1 plus w2, right? And this process continues. Okay, that is selecting the two nodes which have the minimum nodes and then combining them using this process. This process continues until you have only one node left, right? Now, so at every step you have to find the two nodes which has the minimum weights. So what you can do, you can order the characters in the ascending frequency. Okay, so E has the highest frequency, 10. Okay, then T 705A3. Okay, so first we arrange all the characters in the order of their increasing frequency, right? Then you select those two characters which has the minimum frequency. So we will select A and O, right? So the two characters which are at the bottom of the list, because the list is not sorted. So we have selected A and O. So we will combine them using the Huffman process. Okay. So we will create a subtree. Okay. We will create a new parent node. Okay. And the left and right children of this parent will be node A and node O. The weight of A is 3. The weight of node A is 5. Okay. So the weight of the parent of these nodes will be 3 plus 5, 8. Okay, so we have labeled these parent nodes as star, right? Now this entire subtree is now considered as a node, and its weight is 8, 3 plus 5. Okay, now since we have used node A and node O, so we will remove them. Okay, and a new node will be added, star, with weight of frequency equal to 8. Okay, now we have only these three nodes, T, star, and E. Okay, this is star with frequency equal to 8. Now, now select two nodes with minimum frequencies with minimum weight. So node T and this star will be selected. Okay, and they will be combined. Okay, so T and this sub T will be combined. A new parent node will be created, and its weight will be equal to the weight of T and the weight of this old sub T. 7 plus 8, 15. Okay, then again, what we'll do, since this T and this star node have been used, so these will be removed and the new node will be added to the list in the correct order. The weight of the new node is 15. Okay, so 15 will be, so this, the new star will be added after E. Okay, now you have only two nodes left. Okay, so these two nodes will be used and removed from the list. Okay, so this entire tree and the node E and this entire will be used to combine using the Huffman process. Okay, so the what will the weight of the parent? The weight of E is 10 and the weight of this subtree is 15. So 10 plus 15, 25. This is the weight of this parent node. And now you are left with only one node, one subtree. So our algorithm is done. Now how to find the codex? How to find the code for each character? Remember that here you can notice that the nodes for the characters are leaf nodes. This is the node for E, this is a leaf node for T, leaf node for A, leaf node for O, leaf node, and all others are internal nodes, right? And those internal nodes are not does not correspond to any character node. Okay, and you can also notice that the number of children for a node is either 0 or 2. For all the internal nodes, the number of children is 2, and for all the leaf nodes, number of children is 0. Okay, so this is an extended binary tree or tree, 0 or 2 children, right? All the internal nodes has exactly 2 children, and all the leaf node which corresponds to the characters has 0 children, no children. Okay, so to obtain the codes, what we do, we assign either 0 or 1 to an edge. For all the left edges, we can assign 0, and for all the right edges, we can assign 1. Okay, so 0, 1, 0, 1. Okay, now to find the codes for a character, we follow the path from the root node to that node, and we write the label of the edge, assign label of the edge along the path. Okay, so for E, what is the label? 0. Okay, for node T, what is the label of the path? Okay, this is the path. So here we have 1 and then 0. Okay, for A, the path is this. So we have 1, 1, 0, and for O, the path is 1, 1, 1. Okay, so these are the codes obtained using the Huffman algorithm. Okay, you can see that the number of bits varies. Okay, earlier we have used exactly 2 bits for each character. Now the number of bits for E is 1. Number of bits of the code, number of bits in the code for T is 2. For A on O, it is 3. Okay. the frequency of E is the highest, 10. Okay, so the number of bits is the lowest. The frequency of A and O are largest, so number of bits in the code of A and O is the largest, 3. Right. Now find the total message length. The total message length is, E is used 10 times, so 10 into 1, okay, because only one bit in the code for E. Now T is used 7 times, okay, and its code length is 2. A and O. A is used 3 times, its message length is 3, and 5. O is used 5 times, its number of bits in the corresponding code is also 3. And this sum is equal to 48, less than 50. Okay, so this is a very small example. So the saving is just 2 bits of 4%. Okay, but remember that if the data size of your message is very large, then the saving will also be very large. Okay. Okay, so using the Huffman algorithm, you can find uh, the weighted minimum length of a binary tree, extended binary tree. Okay. Now, okay, one more thing, you can notice that the codes obtained using the Huffman algorithms contains the prefix property. Prefix property means that no code of a character is the prefix of any other code. Okay. For example, 0 is the code for E. So 0 will not be the prefix of any other code. Okay. So 0 is not the prefix of T, A, or O. Likewise, see the code of T is 10. So 10 will not be the prefix of any other code. Okay. So 10. Okay. So here we have 11, and for O we have 11. Okay. So 10 is not the prefix of any other node. Okay, so using this prefix property, converting the binary bits message into the original message is very easy. Okay, for example, say the data transfer is 110.0.10111. Okay, so this data is transferred. Okay, so how will you convert these sequence of bits into the original message? Okay, you start reading the data from left to right. Okay. So first you will find 1, then 0. Okay, so 110 is the code for A. 1, when you read the first bit, 1 is not the code of any character. Then you read the next character 1. 11 is not the entire code of any character. Then you read 0. Now you have 110. Okay, so 110 is the code for A. Okay, so you will write A for these 3 bits. Okay, next you read 0. Okay, now 0 is the code for E. So for this 0 you will write E. Okay, then again you will read 0. Okay, so 0 is the code for E. Okay, then you will read 1. 1 is not the code for any character. Then you will read next character 1. Now it becomes 1 1. 1 1 is not the code of any character. Then you read the next character 1. Now you have 1 1 1. 1 1 1 is the code for A. So for these 3 bits you will write to, okay, stop, and this is the transfer message. Okay, so using the prefix property of the Huffman codes, the data transformation is also very easy. You have to just read from left to right and convert the sequence of bits, the subsequence of bits into the corresponding character using this method. Okay, so this we have already discussed. Okay, another example. Okay, say now you have these numbers. Okay, and you have the frequencies. Okay, so you can build an extended binary tree using the Huffman algorithm. So what you will do, you sort them in increasing order, then you select the 2 nodes with minimal frequencies, with minimal weights. Okay, so you have 5 and 7. 5 and 7 are frequencies. Node 1 and node 2 with frequencies and 5 and 7 respectively are selected. Okay, so node 1 and node 2 are selected. Okay, and then they are combined. The weight of the combined tree will be 12, 5 plus 7. Okay, and then 5 and 7 will be, node 1 and node 2 will be removed from the list and the new node will be added. The weight of the new node is 12, so 12 will be added over here, right? 12 is added just after the node 3. Okay, then same process is repeated. The same process is repeated until you have only one left. You are left with only one node in the tree. Okay, so you obtain this tree, then you obtain this tree, then you obtain this tree. Okay, so to assign the codes, you label the edges, left and right edges. Each left edge is assigned 0 and each right edge is assigned 1. Okay, then you follow the path from the root node to the node, okay, for which the code is to be found. Okay, for example, the code of for this node will be, okay, this is the path, so the code will be 0 1, sorry, this is 0, then right, and then left, 0 1 0. Okay, so the code for this node is 0 1 0. Okay, that is a sequence of labels of edges which are on the path from the root to that node. This is the final card.